Here is one more question on rotational equilibrium, and in this question we will be looking at rotational equilibrium of a beam or a stick or a rod. Right? In this question we have a meter stick and it's balanced on a knife edge at its center. Right? So let us say we have a meter stick. Let us say this is the meter stick. Right? This would be 0, this would be 100 centimeter, because it's a meter stick and is balanced on the knife edge at its center. That means the center of gravity of this is at its center, right? The center of gravity would be over here, and that is another way of saying that the mass of this scale is uniformly distributed, right? And this is a simple concept, but we need to be clear about it, right? Supposing we have a stick, right, and if its mass is uniformly distributed across its entire volume, then the center of gravity would be at its midpoint, exactly in the center. But if we have a stick wherein the mass is not uniformly distributed, then let us say there is more mass distributed on the right and the right edge of the tube of the stick, then the center of gravity would not be here, but it would be moving somewhere towards the right hand side. So this statement, a meter stick is balanced on knife edge at its center, is another way of saying that the mass of the scale is at the center, is at the midpoint of the scale. Right? When two coins each of mass 5 gram are put one on top of other at the 12 centimeter mark. Here we've been given 12 centimeter mark where two coins of mass 5 gram are put. So the total mass is 10 grams. And they are put at the 12 centimeter mark. 12 centimeter mark always from the zero end. So somewhere over here, right? Here we have a force of 10 GF, right, acting over here at 12 centimeter. This is 0 centimeter, 12 centimeter, this is 100 centimeter. So here we have 10 grams put over here, right, acting at this point. When this is done, the stick is found to be balanced at the 45 centimeter mark. If this is the center, the stick gets balanced over here. Right? So I'm going to show it like this, that this is the balance point, right, where it gets balanced. That means if it is supported over here, it comes in equilibrium. It comes in rotational equilibrium. That means if it is supported over here, it doesn't go in this direction. It doesn't go in this direction, neither does it go in upward direction, neither in this direction. So it is in rotational equilibrium when it is supported at 45 centimeter mark. What is the mass of the meter stick? The mass of the meter stick, as I said, will act at the midpoint, so that this would be 50, and here you would have the mass, and we have to find out this m. Right? I hope you are clear about the background of this numerical, right, with what we have given over here. Now, for rotational equilibrium, we know that for rotational equilibrium, let me use this space, for rotational equilibrium of any object, equilibrium sigma tau is equal to 0. That means the summation of the algebraic sum of all the torques has to be 0. Now let us look at this particular situation and see what are the various torques are acting. To find out various torques, we first need to identify the forces. So we have two forces over here, 10 gram force and this m, mass m over here, which we have to find out. These are the two forces acting on this stick. This is the point of rotation, right? This is the axis of rotation. So I will take all the forces, multiply them with the distances from the axis of rotation. That will give me the torque being applied by this force, and take the algebraic sum. If it's, we know the convention, if it is anti-clockwise torque, we will take it as positive. If it is clockwise torque, we will take it negative. Right? So we'll follow this convention and find out the mass m. Okay, so if we take this particular force, this is the axis of rotation. So this particular force will tend to take this rod in this direction, right? Because it is acting on the left hand side of this axis of rotation. So this will try to take in this direction, and that would mean this is creating an anti-clockwise torque. So plus sign 10 gram force. What is the distance from the axis of rotation? This is at 12 centimeter from here, this is at 45 centimeter over here. So this would be 45 minus 12. This is the torque applied by this. As far as this force is concerned, this will have a tendency to take it in this direction, clockwise torque. So I will assign a negative sign to it. M into the distance from axis of rotation is 50 minus 45. 50 minus 45. So these are the two torques which come into play. There are no other forces acting on it. So the summation of this will have to be 0 if it is in rotational equilibrium, which it is. Okay? So now doing a little bit of math over here. 10 into 33 minus 5m is equal to 0. This will give me 5m is equal to 330, and therefore m is equal to 66.0 grams. So this is how we can find out the mass of the scale. The mass of the scale is 66 grams. So whenever we have equations on or questions on rotational equilibrium, we need to look at all the forces, be clear about which are all the forces acting on this object, find out or identify the axis of rotation, and then take each force multiplied by the distance from the axis of rotation, apply this sign convention, and then whatever is unknown or not known in the equation can be found out. Thank you.